All right, Angelica, can you read us the essential question, please? Perfect. All right. Elvis, can you read us the first I can statement? Perfect. And then Levi, can you read us the second I can statement? Perfect. I'm guessing we didn't take reading inventory last week, right? You did? Okay, never mind then. All right. I was going to give you my Mrs. Ballard tip. Pick nonfiction. If you haven't taken it yet, pick nonfiction. That's coming from the testing guy. All right. There's a lot there. Okay. So I'm going to give you a couple of minutes. I want you to kind of read that to yourself. Read it twice because it looks like there's some italicized and some bolded words. Those are probably important. So read it once, and then I want you to read it a second time and go back through and underline where you think you see some important definitions. Okay. So I'm going to give you like 3-4 minutes right now. Read it twice. Give you about another minute. All right. So the world that we are moving into is polynomials. Okay. Poly means many. So that prefix poly, let me write that out. Poly means many. Okay. So that just means that there's many terms. Okay. We know how many terms by the degree, or we know the degree of the function by the highest exponent. Okay. That's what this was kind of talking about with us. So I would highlight polynomial functions. Okay. These ones are all examples of them, but notice it says they can be categorized by their degree. Okay. So a third degree is a cubic. Okay. So it goes on to say linear 1, quadratic or 2, cubic or 3. We know all of that already. In general, a polynomial function of degree n has this what we call standard form. And that's just the x to the n is what's the highest exponent. X to the n minus 1 is what's the exponent that's below it. So if that highest exponent was a 5, the one right below it would be a 4, and then 3, and then 2, and then 1, and so on. Okay. A sub 0 is just a constant term, and they talked about that in there as well. Okay. You, by no stretch of the imagination, need to know that degree 4 is called a quartic. If it's a nice to know, not a must to know. Okay. I don't know, maybe a Jeopardy question someday. Degree 5 is called a quintic, and then after that, they say they just use the degree we'll just use the degree on most of them. You should know, when I say cubic, you should know what that is. Okay, I expect you to know what a cubic is. All right, so it says use a graphing calculator to graph the polynomial functions, and then use the graph of each function to determine the function's domain, range, and end behavior. Use interval notation for the domain and range. So we're going to explore a little bit, and you'll notice I can shoot this little link out to Google Classroom for you. Those of you that are on the digital copy should just be able to grab that link. Maybe not. Okay. Let me get the link out onto Google Classroom. Sorry. It didn't do what I wanted it to do. Let me go here. It's probably in there. Let me shoot it out there for you. Okay. Normally links work in PDFs, but that's not apparently a PDF enough. All right. Put this in Google Classroom really quick. I'm just going to add it to the notes. So everybody needs to go there, even if you're on paper, because we're all going to explore in this a little bit. So I'm just going to add it to the note pages, the link. Okay. All right, save that one. Okay, so go grab that one. Get it open. I'm going to put, there's a second one. I'm going to put it out there while you're getting that one open. It's a Desmos calculator page, basically, is what it is. One thing I didn't set up. Let's explore one, just explore two. Okay. Okay, so you should be getting a page that looks like that up on your screen in Desmos. Okay. Basically what I did was I made it so that you didn't have to type in all the functions, and all we have to do is just click some buttons to do our exploration. Okay. I have all of Explore 1 in here. Notice there's a little note that says use 6 graphs below for Explore 1A, which means those 6 graphs there. Explore 1B are those 6 graphs. Okay, and I left them both on the same, so if we wanted to see them on the same for some reason, we could. What I would do as you're going through this is if you just click on this button here, notice the graph disappears. Okay, if I click on it, it turns on again. And the same thing, I could turn all of these on, or I could turn off the ones that I don't want to see at the moment and turn the other ones back on. Okay, so I'm going to start with just X. We're going to practice a couple together, and then I'm going to have you do some of the work on your own, because we did work on this last week pretty hard. Okay, all right, let me get back to here. All right, so we have to find, we're doing the function f of x equals x, right? That one that we just had up there, this one here. Okay. What does domain mean? Is that the x values or the y values? X values. Okay, so, and it said interval notation, so we're going to use the parentheses, right? What is the domain of that function right there? What's the smallest x? Negative infinity. What's the biggest x? Positive infinity. All right, so that's what we're going to write. Negative infinity to positive infinity. All right, the range is the y values. So remember, these are x's, these are y's. Okay, so the range is the y values. What's my smallest y value on that graph? Negative infinity. What's the biggest y value? Positive infinity. All right, so negative infinity to positive infinity again. All right. And apparently Mrs. Ballard's parent graph chart has it all in the wrong order. So as x approaches positive infinity, so as we're going to the right, remember positive infinity means going to the right, we need to tell me what's going on with the y. Hold on, I got to get back there. All right, so as we're moving this direction, what's going on with the y? Is it going up or is it going down? Up. So how do I write that? Positive infinity. Good. Okay, negative infinity means as we're moving left on the graph, what's going on with the y? So as I'm moving this direction, is my y going up or down? Down. How do I write down? Negative infinity. We should do really well in the quiz, right? Because we've done this a bazillion times in the past week. All right, That's the first one. There are 5 more there. Okay. And then there are 6 more there. All right. And this little link is the exact same link as it was up above. So what I want you to do, so the next thing you would do is go back into your little graph here. I would turn off this one and turn on this one. So that way you can see a picture of it. Okay. And then you need to write down, fill in what you think the domain and the range is. Okay. And then try to write down the end behavior. So I'm going to give you about 4 or 5 minutes. I want you to do get all 12 filled in. So every single box. Okay. So every single, but this shouldn't be new stuff, right? We've done this a bunch of times. Okay. So I will go through a few of them. I'm not going to do all of them in about 5 minutes. Okay. So everybody's working for 5 minutes. Check it out on your own. Okay. Make sure you do both tables. Okay, hopefully you guys got it all filled out. That's about where we're going to stop there. All right, so here's what I want you to do next, okay? With your table partner, or if there's if your table partner is absent, make a group of 3 or somebody who's across the table from you where it makes sense, okay? I want you guys to compare what you got for the domain, what you got for the range, and what you got for the end behavior on both charts. I'm going to give you about 3 minutes to do that, okay? So right now you're comparing. You might need to work as a whole group. That's fine. Go. I want to hear some discussion. What? Water? Yeah, take the pass. Okay. Okay, let's take a look really quick. Okay. So what did we get for x squared on the first chart? Negative infinity to positive infinity. Okay, and then where did the range start? 0. What was special about 0? What do I have to put? Bracket. Good. And then all the way to what? Positive infinity. Okay, and as we go to positive infinity, it should go to. As we go to negative infinity, it should go to positive as well, right? Everything was going up, right, on that graph. Okay, on the cubic, what was my domain? Was there any single one of those in that chart that wasn't negative infinity to positive infinity? No, they were all negative infinity to positive infinity, right? The domain is the same on all of them. They're all valid for all, not writing very well, all x values, okay? All right. What about on the whatchamacallit, the range? What was the range on that one? Negative infinity to positive infinity, okay? And then as we were going to positive infinity, what it was the end behavior? This should have been positive, right? It was going up. What about on the other side? What was it? What was going on? Negative infinity. Good. All right. What about the range on x to the 4th? Where did it start? Where did it start, everybody? 0. Okay. And where did it end? Should have been positive infinity, right? And then were they pointing up or pointing down? Up. So they should have both been positive infinity. Okay. All right. The 5th power, what was the range? Good. Negative to positive. Okay. And the end behavior, what was, as we went to the right, where did it go? Up or down? Up. Good. Okay. And what about as we went to the left? Up or down? Down. Good. All right. And then where did the 6th power, where did the range start? 0 to positive infinity. Were they both pointing up or both pointing down? Up. Did we see a pattern? Did we notice something about the exponents? I'm going to go in and look at Desmos really quick with you. Okay. So on let's just take a look at these ones here. Don't they all kind of act the same way? They all have the same domain, the same range, and the same end behavior, didn't they? What pattern do we see in those exponents? What kind of numbers are those? Say it louder, I heard it. They're odd numbers, right? So the odd numbers all act the same, and let's check out the even numbers. Okay. Look at the even numbers. Don't they all act the same as well? Come on. Don't they all act the same as well? They all both point. So the thing that we're curious about is, does this also happen when we throw a negative in front, when we change the equation just a little bit? So looking at this next set, was the domain the same on all of them? Did the domain change? Was it still negative infinity to positive infinity? Yes? No? Didn't change. Okay, so they're all still negative infinity to positive infinity. All right. So that's the same. Okay. What about the range? What was interesting, or what did the, on the odd ones, was the range any different than the range on this chart here? Yes or no? Did it still go negative infinity to positive infinity on the odd ones? Yeah. Okay, so I'm just gonna do the odd ones. Negative infinity, positive infinity, because there's obviously a pattern with each kind of set. Okay, let's just talk end behavior on the odd ones. Okay, so I'm going to go back to Desmos actually for just a second. All right, I'm going to go down to my second set of stuff. All right, so I'm going to turn on all three odd ones. Okay, so there's all three odd ones on at the same time. As we go to the right, we're going this direction. Did they go up or did they go down? Ooh, they all went down. So those are all negative, right? Negative infinity. So negative infinity, negative infinity, negative infinity. Okay. Then it's asking us, as we go to the left, I went to the wrong thing. I want to go here. As we go to the left, what's happening? Are they going up or are they going down? They're going up, so they should all be what? Positive infinity or just infinity? But there's still a definite pattern that whatever's going on with the odd ones is going on with all the odd ones, right? Okay. Let's look at the even ones. I'm going to go back here and I'm going to turn these off. Okay. So with all those even ones, what's the lowest y value? Negative infinity. Nice work. Okay, so negative infinity on all of them, right? What was the highest y value on all of them? It's 0. Good job. Okay. So it ended at 0 this time. So that was the big difference, is when it went below the axis, it ended at 0. Okay. Did they both point up or both point down? They all pointed down, so they all went to negative infinity on the end behavior. But definitely a pattern with all the evens as well. Okay. All right. So let's talk about, the next question is asking us to generalize the results of what we just did. Okay. So basically, we're looking for some patterns. So how can you generalize the results for this explore? For f of x equals x to the n and f of x equals negative x to the n, where n is a positive whole number. So notice we weren't working with negative exponents, right? We weren't working with fractions. We're just working with positive whole numbers, okay? So there were basically, well, actually, what was the domain of everything? Yeah, domain is always negative infinity to positive infinity, or just infinity is fine. So it didn't matter which one we had, the domain was always the same. Everything worked, okay? All right, the range, so let's talk about even and odd, right? So odds, odd exponent, I'm not going to write in sentences, even exponent. I'm just going to write some categories here. Okay, so on an odd exponent, what was the range no matter what? Negative infinity to positive infinity. Okay, always. All right. Then we always knew that if, let's just talk about the end behavior in general, okay? On the end behavior on an odd, did each end have the same end behavior, or did it have different end behavior? It was different because one always went to positive and one always went to negative, right? So it didn't matter which one was. One of them was first, one of them was second, but they were always opposite end behavior. So I would say had opposite. That's not writing. Opposite end behavior on each end. Okay. On evens, our range. Either it was negative infinity to 0 or 0 to infinity, right? It depended upon if it was positive or negative in front. But it was only one of those two things. What about on an even? What happened with the end behavior? Were they the same or were they different? It was always the same, right? So the end behavior was always the same. That's two words, the same. Not one weird word. I'll fix it. It looks like one weird word. Always the same. Okay. I'll give you a minute. I know some of you are still writing. I'll give you a minute to catch that up. Okay. We're going to look at the second explore. So that was just talking about stuff we've been talking about for a week now, and actually really for a semester, because we talked about all that stuff first semester. Okay. All right. This next thing is going to introduce some new vocabulary, but it's extremely important vocabulary. In fact, I'm sad I didn't do this. In about another week here, I'm going to use this vocabulary again in calculus. So I'm sad my group in calculus did not get this last year. When you're reading through this, okay, I'm going to have you read it 2 times, just like we were doing before, okay? I want you to make sure that you find the definition for intercept form. Okay, you don't have to write this down. I just want to make sure that you know what I want you to see. I want you to figure out what a turning point is. Okay. I want you to be aware of the word global. The word, hold on a second, I'm going to look here. The word absolute. The word local. And the word relative. Okay. So read it once and just read it all the way through. Don't underline anything. On your second read, I want you to find those 6 things and make sure you get them underlined. Okay, and see if you can find their definitions in that. Okay, so I'm going to be quiet for like 3 or 4 minutes. You do read twice. Okay, hopefully you're on your... I'm going to give you about 30 more seconds, and then I'm going to go point out some stuff in there, okay? Okay, let's take a step back for just a second, okay? Let me think about this. Let me do this really quick. X squared. Okay, so let's say I had that, all right? Good old quadratic, right? We would say, okay, we know we can factor that. I need two numbers that multiply to 2 and add to -3. What are they? What do we think? -2, -1, which means I would rewrite this as x minus 2 times x minus 1. These two things are called linear factors because our exponent is 1 and a line's exponent is 1, right? So that's why they're saying the word linear factor in there, okay? The number of linear factors you have is the degree of the function. So we had 2 linear factors. My degree was 2. Because eventually I could multiply these back together, and remember, I would add my exponents. I would get back to the squared, okay? And this thing here that we had is what we call the intercept form. I can graph it based on this, or at least I can start. I got some really good information in there to start graphing it, okay? So hopefully you found that this thing here is the intercept form of a polynomial. All they're saying is I'm just going to expand that all the way out, and it's going to look like what we do with the quadratic, only it might have more terms, okay? So then it says in here, a graph must move away from and then back toward the x-axis between each pair of successive x-intercepts, which means the graph has a turning point between those intercepts. So that's because the graph is moving away from and back towards the x-axis, okay? So it's going to turn, right? Think about a parabola. It's going to go down, and then it's going to turn and move away, okay? We're just going to have more of those turns with a polynomial, okay? Instead of crossing the x-axis and the intercept, it can be tangent to the x-axis. So it can be tangent. We're going to see what that looks like soon, okay? Sometimes that point of tangency becomes a turning point because the graph must move toward and then away from the point of tangency. Okay. Huge vocabulary in this next section. I'm going to blow that up. I should have blown it up sooner. Sorry. So each turning point is a maximum or minimum value. If you haven't done that, highlight that. Okay. It's either the top of a hill or the bottom of a valley. That's what maxes and mins are. Okay. The max or min is called a global or absolute if it never takes on a value that is greater than the maximum or less than the minimum. So global and absolute are interchangeable words. It's been trending on the AP Calculus test to call it absolute, okay? But both are interchangeable. And that just means it's you cannot get anything higher than it on the graph, okay? So if I were to draw a little sketch here, okay? Other than maybe, okay, so this part right here, I don't like that, what I drew. I'm going to try that again, okay? All right. This part right here is slightly higher than the other one, right? That would be my absolute. I cannot get higher than that. That's an absolute maximum, okay? If it was down on the bottom, it would be an absolute minimum, all right? Then they talk about local maximum or local minimum. They can also be called relative. So local and relative mean the same thing. We tend to, on the calculus test, see more relative now than local. So that's the word that I would probably use more, but they are interchangeable. You have to know both, okay? And then that basically means is a maximum or minimum sum or within the interval, within some interval around the turning point. Okay. It isn't necessarily the global. So this one would be a relative min, and this one would be a relative max, because it's around all the points surrounding it are a little bit higher. On this one, all the points surrounding it are a little bit lower. Okay. All right. A lot of vocabulary in there today. All right. So we're supposed to use our graphing calculator to graph the cubic functions and then use the graph to answer each of the following questions. We're going to get as far as we can. You might not be able to finish all of the homework. We'll see how it goes. So do as much of it as you can tonight, and then you can be able to finish it up after we do this tomorrow again. Okay. All right, so let's look at, so go back into Google Classroom and grab that second file that I put out there. So grab Explore 2, okay? And get that one open. Okay, so I split it up again. The first 3 are for Explore 2A. The second 3 are for Explore 2B, okay? So that we can quickly see the graphs and we don't have to put all of that in there ourselves, okay? All right, so use a graphing calculator to graph the cubic functions. F of x equals x cubed, f of x equals x squared times x minus 2, and f of x equals x times x minus 2 times x plus 2. Then use your graph of each function to answer the questions in the table, okay? So what they mean about distinct factors, okay, is meaning that it's different, okay? How many different factors does it have? In x cubed, there is one distinct factor. It's x, okay? Because it's got x 3 times, right? If I were to expand that, it would be x times x times x. All right? Looking at the second one, we have x times x minus 2, right? That's what x squared means. But as far as distinct factors, ones that are different, there's the x and there's the x minus 2. So there are 2 distinct factors there. All right. What about the third one? How many distinct factors? 3. So each one of these little things is called a factor, right? We've seen that before. That's what factoring is each one of them is a factor of it. All right. Let's look at what the x cubed looks like. So I'm just going to go down the first column. We'll see if we can get through that first column here together. So I'm just looking at this graph. So my cubic graph. All right, and we're going to answer questions about the cubic graph. What are the graph's x-intercepts? X-intercepts are where it crosses the x-axis. Okay, so what x value does it cross the x-axis at? 0, just 0. So just x equals 0. So x equals 0. All right. It asks, is the graph tangent to the x-axis, or does it cross it at the cross the x-axis at each x-intercept? So tangent means, and we'll see hopefully one that's tangent here in a minute. Tangent means it's going to like bounce off, whereas crosses means it goes through it. So is it tangent or does it cross? It crosses. Good. All right, so it crosses at x equals 0. That says crosses. And no, it doesn't look like it, but it does say crosses. All right, it's next asking us how many turning points does it have? So does this one have any turning points where it goes from going up to going down or going down to going up? Does it change direction? This one doesn't change direction. You're going to see what it means by changing direction in the next one, okay? So that one doesn't change direction in this case. What's going on? Okay, so none on this one. All right. It's asking us if it has any global maximum values, or how many globals, how many local maximums, and then how many global and local minimums. That's what the next 2 boxes are, okay? In this case, there isn't like that turning point. You really can't have a global or a local max or min without that turning point, okay? So because it's always going up and always increasing, there are no locals or no global maxes or mins, okay? So we would say none on both of these. Okay. Let's turn off that one and turn on the next one. Still a cubic, right? It still has the same characteristics of a cubic. Its domain is a negative infinity to positive infinity. Its range is negative infinity to positive infinity. And its end behavior is acting like a cubic. But a very different graph this time. Okay, do you see how it makes a hill and makes a valley? Okay, so now we've got some turning points. We've got some other exciting things going on there. Okay, all right, so let's see if we can answer the questions now. What are the graph's x-intercepts? So anytime it touches or goes through the x-axis, let's look at that. So where does it touch or go through the x-axis? What x values? 0 and 2, good. Okay, so at x equals 0 and x equals 2. Okay, so now we're supposed to determine, does it cross or is it tangent? Okay, so at 0, does it cross or is it tangent? See how it goes up and it bounces off the x-axis and comes back down? That is an indicator that it's tangent. Okay, whereas this one, see how it goes through the point? That's a crosses. Hopefully we see the difference. Okay, all right, so we're going to say crosses at x equals 2, tangent at x equals 0. All right, let's count the turning points. So how many times does it turn directions? It goes 1 turn there and then 2 right there. Okay, so it goes from up to down and then down to up. Okay. All right, so 2. Then it's asking how many global max, local min, local min. Okay. All right, so global means it has to be the highest. Okay, so let's just talk global, both max and min for a second. The highest, isn't it going to infinity? And the lowest isn't going into infinity. So it doesn't have any global or absolutes. Okay. As far as locals go, isn't that one a local or a relative max? And this is a local or a global or a relative min. Okay. We could cheat a little bit. 1.3 and 0. Okay. So let's write those down. Okay. So, it doesn't tell us what we have to identify. So 1 local max, 1 local or relative max, and 1 local or relative min. Okay, we get out is 58, right? 57. Okay, we're gonna stop there. We will continue. You should be able to do at least the first 4 or 5 questions on the homework with what we've done. So don't neglect it. Get that part done, even if you can't finish the whole assignment yet. Okay? We will pick it up from here tomorrow. Lots of vocab. Sorry, it just is the way it